Whenever you have this on, this capacitor gets charged, right? So, so that means you need to have this circuit. Now, what happens in the dead time? In the dead time, I guess you don't really have charging. Dead time, both of them are off.
Sorry,
So your
you're not.
screen is not sharing.
Yes,
Oh.
that's.
Oh, all right. Can you see my screen?
Yeah.
Yeah. So this is your top MOSFET. This is your bottom MOSFET, and this is your boot capacitor. Okay? And this boot capacitor is getting charged only when the bottom MOSFET is on. So that means it's critical that the bottom MOSFET be on for this to get charged. In the dead time,
शेड्यूल आहे ते 2 मे 4 दिवसाचा कोर्स ऍक्च्युअली पण 1 मे सुट्टी लंच इन्क्लूड नाही
we have some noise here in the background. Sorry, can we mute? Okay, so the dead time, what happens at the dead time? So in that time, there is no charging of the boot capacitor. But the interesting part is, if you have a large enough boot capacitor, you can probably go off for several cycles before it requires a charge. That may not be practical to do, so you end up charging the boot capacitor every cycle when this MOSFET is on. Now, let's say if you have a very small capacitor and you are running at 97% duty cycle or 99% duty cycle. So you have to think about, in 1% time this guy is on, is that enough time to charge your boot capacitor? So it's important to monitor your voltage between these 2 points. Okay, so that's a very good point, Konstantinos. Thank you for bringing that up. Any questions? Is it clear? All right, let's go back to our PowerPoint. All right, so you have, this is the charging path for the boot capacitor. And if this boot capacitor is not charged, it will not be able to drive the top MOSFET. Okay, something to keep in mind. Now, I can use that concept also to deliberately discharge the boot capacitor, whereas I can disable the top MOSFET if I don't want to enable it. That's an option you have in your hand of how to disable the top MOSFET. Apart from the signal, you could discharge the boot capacitor and not allow it to charge. Okay, so let's go to, essentially, we talked about the bootstrap capacitor. So you have your gate to source voltage essentially becomes greater than your drain to source voltage plus your threshold voltage applied to the gate in order to turn on, right? So your bootstrap capacitor floats quite a bit higher than your bus voltage. It has to, in order to charge, in order to drive the top MOSFET. Okay, so bootstrap capacitor is simple and low cost. Problematic when negative voltage is present at the source of the switching device. And here is the drive circuit operation. Essentially, you're going to charge, this is your charging path through the bottom MOSFET, and then you're discharging it essentially when you turn this Q1. Okay, so it gets a charge through your VB and this VS and along with your. All right, so these are some calculations. What is the correct value of a bootstrap capacitor? So if you look at what is the boot delta we need, it is given by the VDD, which is your supply voltage, not the DC bus voltage, but your control voltage, then your forward voltage drop, and then your gate to source minimum voltage required to turn it on. So this is the maximum allowable voltage drop, depends on the minimum gate drive voltage for high side switch to maintain.